In order for the pump to operate properly, the thrust must be offset. On some pumps, the thrust is offset by using a thrust bearing or a device known as a balance piston or balance drum. On other pumps, the thrust is offset by the arrangement of the impellers. This pump has a balance piston. During operation, some of the fluid leaving the pump flows along the shaft and exerts pressure against the balance piston. That pressure tends to force the pump shaft away from the suction eyes and reduces the total thrust. Any fluid that passes by the balance piston is returned to the suction side of the first stage. Now on this pump, the arrangement of the impellers is used to offset axial thrust. Process liquid enters the first stage impeller from both sides, so the pressures on both sides of the impeller are equal. The suction eyes for the second stage and third stage impellers face in the opposite direction from the suction eyes of the fourth stage and fifth stage impellers. Since the forces caused by axial thrust are in opposite directions, they tend to cancel each other out. As a result, axial thrust in this pump is kept to a minimum. In this topic, we looked at the basic operation of several types of centrifugal pumps, including single-stage pumps, vertical pumps, and multi-stage pumps. Now let's try some practice questions that relate to this material. Inside all centrifugal pumps, an impeller creates centrifugal force to move liquid through the pump. Impellers can be designed in different ways, depending on factors such as the type of liquid being pumped and the amount of pressure increase that's needed. The impellers used in centrifugal pumps can be divided into three categories: closed, open, and semi-open. This impeller is a closed impeller. Its vanes are enclosed by shrouds on both sides. The shrouds direct the flow of liquid between the vanes. Closed impellers are often used with low viscosity or thin liquids. Liquids that are thick or contain suspended solids could clog a closed impeller. With those types of liquids, an open impeller could be used. This is an open impeller. As you can see, this impeller has no shrouds to direct the flow of liquid. While this design helps prevent clogging, it's less efficient at moving liquids than a closed impeller, since the flow of liquid is not directed between the vanes. Open impellers are used to pump thick liquids or liquids with solids such as slurries, and closed impellers are used to pump thin liquids. Semi-open impellers can be used for pumping thin liquids since there is a shroud to direct the liquid between the vanes. They can also be used for heavier liquids and slurries since they minimize clogging. Impellers can also be classified in other ways. For example, closed impellers can be further classified as single suction impellers or double suction impellers. This impeller is a single suction impeller. It has only one suction eye, so there's only one place that the liquid can enter the impeller. Single suction impellers are fine in applications where the pressure change across the pump is relatively low. In applications where the pressure change is higher, large amounts of axial thrust are created and must be offset. To minimize the effects of the axial thrust, some centrifugal pumps use a double suction impeller. A double suction impeller has two suction eyes, so liquid can enter the impeller from opposite directions. Because of this, the pressure on both sides of the impeller is the same, and axial thrust is minimized. No matter what type of impeller a centrifugal pump uses, the liquid being pumped gains pressure as it slows down to fill out the increasing volume of the volute. Radial thrust is a type of thrust that tends to move a pump shaft perpendicular to its axis. In a pump with a volute, the thrust is created by the difference in pressure across the volute. Now, some centrifugal pumps are equipped with a component that accomplishes the same speed-to-pressure conversion as a volute, but minimizes radial thrust. It's called a diffuser. A diffuser consists of a series of stationary vanes that surround the impeller. When we look at the vanes closely, we can see that the distance between the outer tips of the vanes is greater than the distance between the inner tips. As a result, the vanes create a series of small volutes all around the impeller. This arrangement of vanes balances the radial thrust around the impeller. Pumps require some type of seal between the pump shaft and the casing to keep process liquids in and contaminants out. Some pumps use packing to seal around the shaft. Other pumps use a device called a mechanical seal. On this cutaway of a typical mechanical seal, we can see the two basic parts: a stationary element that's attached to the pump casing and a rotating element that's attached to the pump shaft. Each element has its own seal ring. The two rings are positioned close together to form a seal that has virtually no leak-off. To prevent the seal rings from being damaged, some type of lubricant must be supplied to them. In some applications, the process liquid being pumped is used as the lubricant, but that's not always the case. When the liquid being pumped could be hazardous if the seal fails, or if it contains abrasives or other solids, such as in a slurry, an external liquid may be used to lubricate the seal rings. Many facilities use an independent system to provide lubricating liquid to the mechanical seals of several pumps. This is a simplified diagram of a typical sealing system. It provides lubricating liquid to the mechanical seals on all of the pumps in a process. The system consists of a storage tank, a filter, a supply pump and a backup supply pump, a low-pressure switch, a pressure regulator for each mechanical seal, and a flow meter for each mechanical seal. For this process, an oil is used to lubricate the mechanical seals. During operation, the supply pump draws the oil from the storage tank through the filter. The filter removes contaminants from the oil to prevent damage to the sealing system pumps and the mechanical seals being supplied. The pump supplies the oil to the pressure regulators on each supply line. The pressure regulators control oil pressure and the amount of oil flow to each of the mechanical seals. The flow meters allow the flow to the seals to be monitored. If the supply pump fails to deliver the oil at the correct pressure, the pressure switch will sense this condition and automatically start the backup supply pump to restore pressure. At the mechanical seal, the oil lubricates the seal rings. The oil then passes by the seal, flows into the return header, and is sent back to the storage tank. From there, the oil can be reused.